proofs, and the word deduction means that you deduce from some results that you assume to be true. So you start with some known knowledge, something that you are already familiar with, or a rule that you already know. Assuming that the rule is true, you start deducing the consecutive results. So let's look at some of the examples, and in some cases we will prove that these are identities, which means they are true for all values, and in some cases they will be true for only specific values. Like the first example we see, the question says verify whether x square plus 1, so this is my LHS, is same as 2x plus 4, which is my RHS, right? And I want to verify it first for two specific values. One is x equal to 3 and another is x equal to minus 1. So I'm going to look at LHS for x equal to 3, and it is 3 square plus 1 is 10, and RHS is 2 times 3 6 plus 4 is also 10. So yes, it is true for x equal to 3. Let's look at for x equal to minus 1. The LHS is minus 1 square plus 1 is 2, and the RHS is 2 times minus 1 plus 4 is also true. Right. So therefore, for x equal to 3 and x equal to minus 1, this expression x square plus 1 is equal to 2x plus 4, right? For x equal to 3 and minus 1. However, the question says explain why it's not an identity. So it is usually an identity when it is true for all values. So let's substitute any other value, for example x equal to 2, and now let's see what LHS is. So 2 square plus 1 is 5, and RHS 2 times 2 is 4, 4 plus 4 is 8, and LHS is not equal to RHS. So even one example, if it contradicts with the rule, then it's not an identity. So that's my explanation, that I use any one value which contradicts that result of LHS equal to RHS, and that's enough for me to say it's not an identity. So what are identities? Let me give you an example. You might have already learned some basic algebraic identities like a plus b the whole square, and where you say it's a square plus 2ab plus b square. How do I get it? Well, I do the multiplication of this binomial expression, and most of you are familiar with the rule of distribution. So a times a plus b times a plus b, every term of the first bracket is multiplied with every term of the second bracket, and that's how we get to the result a square plus 2ab plus b square. Now this is an identity because any value of a and b, be it positive, negative, fraction, decimals, this will hold true, and that's the reason it's called an identity, right? So anytime you are supposed to prove that it's not an identity, even if for one value it is not holding true, then you have already proved it. Let's look at the second result. The second result says use consecutive simplifications, and we have to prove that the LHS equal to RHS. So whenever we are doing proof questions, remember, you start with one side of the equation and you reach to the other side. Which side you start from doesn't matter, but you cannot assume them to be true because the question is show that. There is also a condition given here, b is not equal to plus or minus 2a. Why is this condition important here? What happens if b is equal to minus 2a? On the right hand side, if b is minus 2a, the denominator would become 0, and division by 0 is not a possible operation, right? It makes the expression undefined. Even on the right hand side, if b is equal to plus or minus 2a, then b square will become 4a square and the denominator will become 0. Therefore, it's not allowed. Okay, which is why this is a condition given to you. So whenever conditions are given in questions, be particularly clear about what is the reason for it, because there might be explanation questions later or reasoning questions that you may be asked on it. So the expression on the LHS is what we start with: 2a square plus ab minus b square upon 4a square minus b square. That's the expression we have, and I want to simplify it. So let me look at what simplification I need. So I will go to my RHS and see, oh, denominator has only 2a plus b. So let me change my denominator here. My denominator looks of the form difference of two squares, and difference of two squares can be written in this format. A square minus b square is a plus b into a minus b. So I'm just going to do that. And on my right hand side, the denominator only has 2a plus b. That means somewhere 2a minus b is getting cancelled. So let me go back to my numerator and try to rearrange the terms. Instead of 2a square, I'm going to write it as a square plus ab plus a square minus b square, right? So there are two a squares and I'm just distributing it and rewriting it. So a is common here, a plus b, and I'm rewriting this also as a plus b into a minus b. Okay, so this is what I have done. I have written 2a square as a square plus a square and then taken out some common factors. My denominator remains the same. And now let me see, is there anything further common in my numerator? Well, a plus b seems to be common, and what remains in the bracket is a plus a minus b upon 2a plus b times 2a minus b. Well, it's very easy to see that numerator and denominator have a common factor, 2a minus b, and I am able to cancel it. Remember again, why I could cancel this is because b is not equal to plus or minus 2a. If it was equal, then I'm as good as cancelling zeros, which is not correct. It's not mathematically possible to divide by 0, and therefore anytime you cancel out factors, you have to be sure that that factor can never be 0. And therefore it is a plus b times 2a plus b, which is what your right hand side was. So I am assuming true. Now what is the why is this a deductive proof is because I assume the rule of 4a square minus b square is 2a plus b into 2a minus b as known. From that known rule I deduced the next result, and therefore it is deductive deductive proof. Let's look at the next question. The question says any integer, if it's an even number, then I can write it as a multiple of 2. So 2n is a generic form of writing an even number, and 2n plus 1, that means 1 more than an even number is an odd number. Prove that sum of two even numbers is even and sum of two odd numbers is also even. So again I'm going to use a generic form of the even number. So is it only even numbers or square? Sum of even numbers, correct. So let's start with, so there one of the even numbers can be 2m and another can be 2n, and I know that why I'm writing it as 2m and 2n means m and n are integers values, and they are all, if it's an even number it must be a multiple of 2. Therefore 2m and 2n are in general an even number. If I sum them up, then I can take 2 common and m plus n. M and n were integers when we started with, so m plus n is also going to be an integer, and 2 times m plus n will definitely be an even number. So sum of two even integers is resulting in an even number. What if it's an odd number? So an odd number would be written as 2m plus 1 or 2n plus 1. Adding them results in 2m plus 2n plus 2. Can again take 2 common, which means m plus n plus 1. If it's a multiple of 2, it must be even. So again I could prove that even if I start with 2 odd integers, the sum is ending up with a even number. Again, what is that I assumed? Why is it deductive proof? Because I assumed my knowledge of writing a general even number and odd number, and from there I deduce the rest of the result, and therefore it is deductive proof. Next is by using an identity. You remember, identity means it is true for all values. So x plus 1 the whole square is x square plus 2x plus 1. That's an identity because for any value of x it is true. Using that identity, prove x plus 1 the whole cube is okay. So this is known to me. X plus 1 the whole square is x square plus 2x plus 1 is known to me, and I want to show x plus 1 the whole cube, which means x plus 1 times x plus 1 the whole square. So x plus 1, and I can always assume this result because that's what the question says. Use that result, and now I'm going to use the distributive law. So x cube plus 2x square plus x square plus 2x plus 1. Collect the like terms. So x cube, the x squares get added, the x's get added, and 1. And that's how I could prove that x plus 1 the whole cube. You have will also be studying binomial expansion, where you will see the rule of expanding binomials with any power, not just the smaller numbers, which you all are more familiar with. And the last, and they are also asking us to verify this result for x equal to 1 and 2. I'm going to skip that part because that's not very hard for you to do. Let's do for maybe x equal to 2 for this expression. 2 plus 1 the whole cube, which is 4 cube is 64. And if you look at here, 2 cube is 8, 2 square is 4, 4 times 3, 6 plus 1. And oh, I'm sorry, 3, this is 2 plus 1, 3 cube, which is 27 and not 64. And here also you see that 12 plus 8 plus 6 plus 1 is 27. So I'm verifying that the rule what I wrote was true for x equal to 2. And I use this result to find 101 the whole cube. So I'm going to write 101 as 100 plus 1 the whole cube, because it was to be written in the binomial format of x plus 1. Why 100? Because 100 powers are very easy to find out. What was the identity I wrote? That it is equal to x cube plus 3x square plus 3x plus 1. So x cube is 100 cube plus 3 into 100 square plus 3 into 100 plus 1. So 100 cube, 6 zeros, and 1, 2, 3, 4, 5 and 6, correct, plus 3 and 4 zeros, and plus 300 plus 1. So it's easier to add numbers like these than multiply, right? That's how the identity was useful to us. So that's an application, is that identities are sometimes useful for mental math.